Welcome back to lecture 19.1, where we're going to continue our discussion of entropy. So just as a reminder, in Fin, we're covering chapter 5. So we've been discussing chapter 5, kind of doing around 5.6 and 5.7. So we're going to do 5.7 in this lecture. Okay, so this is going to be about TS diagrams. Okay, so before we talk about TS diagrams, though, let's just remind ourselves what we've been talking about in terms of entropy. So we defined this integral around a closed loop of dq r over t to be our change in entropy. And we said very clearly that for a reversible process, right, that this was going to be equal to 0. But this was, generally speaking, greater than or equal to 0, where we said that the change in entropy can be thought of as the change from one state B to another state A, right? Because, which is the integral from A to B of dq over t. And that this always was greater than equal to 0. So in a closed loop, so a closed loop was 0 for an isolated system. And so remember, these equal signs are only equal to 0 for reversible isolated processes. Okay. So if the system is not reversible or not isolated, the entropy is greater than 0, right? It's greater than 0 for not reversible or not isolated. Let's just write it. Reversible or not isolated processes. Okay, so we're going to start class for class number 19 with an example. And the example we're going to do is going to be the following. So example in class, we're going to have two objects that are going to be at T1 and T2. And we're going to ask, when we put them in the thermal equilibrium, what happens? And we should be able to calculate TF. So what we're going to be able to do is calculate TF, calculate the energy change in this process. We're also going to calculate the entropy change in this process. Okay, so we're going to do that example in class. So we're going to skip it in the lecture. Now, one thing to note is that for a reversible process, we have defined our exact differential for our entropy. Remember, our entropy is a state function. It is only depending on the state. And we've said, well, you know, it's exactly this integral when dq is a reversible process. But when it's irreversible, we can't have this. It's not exactly equal to this. So there's this Clausius inequality. But for a reversible process, we can actually define the exact differential for ds, right? Or another way to say that is that we can actually use our knowledge of the entropy to find this work, as if the work was always, to find the heat, as if these processes were always reversible, right? All right, so this is kind of analogous to the work is minus dW is minus PdV. Right? So this is an analogous kind of statement. So we can also say that Q reversible is the integral of TdS. Just like we had the dW was minus PdV, and our work was minus the integral of PdV. Okay, so now we have kind of an equivalent form for the heat that we did for the work. So when we wanted to calculate the work, what did we look at? We looked at PV diagrams, right? So we can analogously make TS diagrams. So that's what we're going to look at now. We're going to look at TS diagrams. Okay, so remember, so just like in our PV diagrams, our work was going to be the area under the curve. On a TS diagram, the heat is clearly going to be the area under the curve. Remember, this is only possible for reversible processes, right? So that's only for reversible processes. Okay, so let's look at our classic example of an ideal gas. So let's look at an ideal gas and ask what happens for, let's say, these various processes. Let's do isothermal thermal expansion. All right, so on our PV diagram, what did it look like? So we went from state 1, let's just call it A to B. So from A to B, we had some isothermal expansion. Let's say call it from V0, from the initial to the final. And then the work was the area under that curve, right? So for isothermal expansion, we can, now that we know about the entropy, and if we can calculate the entropy, because the entropy is a state function, we can now calculate the heat that's done in this process, the heat evolved in this process, by looking on a TS diagram. Okay, so in a TS diagram, what's going to happen? Well, we know that the temperature is going to be constant, going from state A to state B, right? The entropy is going to increase when we go from S0 to SF. And we know that the entropy is going to increase because we just did an example in class, this one, where we saw that the entropy increased. We also know that the entropy is always going to increase in a process. Okay, so in this process here, the area under the curve now is the heat. But it's QR. It's the heat for this reversible process. Remember, we could have undone this because we're not isolated, right? I mean, this one's isolated, but it's isolated and reversible, so we can actually undo this. All right. What about adiabatic expansion? All right, adiabatic expansion. Well, when we did it on a PV diagram, we had some initial volume, some final volume, and we had a curve similar to our isothermal, but with a steeper slope. Remember? So the work in this process looked like that. Okay, so you might think, oh, adiabats and isotherms are pretty similar, right? Well, on a PV diagram, but on a TS diagram, they really couldn't be more different, right? So what happens in an adiabatic expansion? Well, dq is 0, right? So ds is 0. And so under adiabatic expansion, we're going to stay at the same entropy. Let me go from T, let's call it T0 to TF. There's no heat evolved, so Q is 0. Okay, let's put those together for a Carnot cycle. So a Carnot cycle of course on a PV diagram was an isotherm to an adiabat to an isotherm to an adiabat, remember? And the work was the area under the curve. We know that we had always heat coming in here. This was QH at TH. And this was QC at TC. Let's just label these A, B, C, D as our standard practice. Now, what about on a TS diagram? What does this look like? Okay, well, first thing that's going to happen is we're going to be at a constant temperature, TH. So from state A to state B, we were at constant temperature. State C to state D, well, we were along an adiabat, so it's a straight line down. We came back along TC to point D, and we came back up. And so the heat that's evolved is the net difference between QH and QC, right? So here let's call it delta Q, because delta Q is going to be QH minus QC. It's really the net heat is the area under the curve. Okay, now it's interesting to note that this is for, we thought about it for an ideal gas, but it's actually this shape is true for any Carnot cycle. Because every Carnot cycle has those same factors, right? Not just for an ideal gas. Remember, just like we've said before, that we can rewrite these things instead of Q's as T's for Carnot cycles. Okay, so every Carnot cycle will be identical. Okay, so that's what we're going to do for our TS diagrams. Now we're going to go back and we're going to talk a little bit more about some interesting processes that are going to lead us to some new physics.